Hi students, and welcome to Lecture 9 of the LN 2016A Electronics 1 course. I'm your lecturer today, Mohammed Dango, and we'll be covering the capacitor filter. In today's lecture, we'll be recapping the power supply, and then we're going to focus really on the capacitor filter, starting with the schematic, operation, going on to the current, the ripple, and finally the design. Now, if you get stuck, remember this can all be found in your textbook, chapter 2, pages 75 to 81. And remember, students, anything said or done in this lecture can and will probably be used to examine you in your test and final exam. So recapping our power supply, you know this, starting off with the transformer, which is the first component of our power supply. We've seen that we can have two types of transformers, just a normal one, as you see in this schematic here, or we can have the center tapped transformer, which basically splits the secondary half of the transformer into two halves. After the transformer, we go into our rectifier circuit. Here we have the full wave bridge rectifier and we have the half wave rectifier circuit. We also have the full wave rectifier circuit with the center tap transformer. And we see that we take our AC signal from our transformer and we rectify it to get this output waveform from our rectifier. And then after the rectifier circuit, we move on to the capacitor filter, which is basically a smoothing capacitor, and that has some sort of a ripple voltage, which we will learn about in the lecture today. And finally, in the next lecture, we'll be going through the voltage regulator. So the capacitor filter, as we mentioned, that's the focus of today's lecture. It comes after our rectifier circuit, and we go from this pulsating DC to more of a ripple DC voltage. Students, the first thing we need to know is exactly where to place our capacitor filter in our various circuits. And we can see here from the half wave rectifier circuit, the center tapped full wave rectifier circuit, and the full wave bridge rectifier circuit that the capacitor is placed in the same position in all three schematics, and that is at the output of our rectifier circuit in parallel with our load resistor. And now that we know exactly where the capacitor goes, let's focus on just two of our circuit schematics to try and understand how this capacitor operates. So we'll be focusing on in this lecture the half wave rectifier circuit and the full wave bridge rectifier circuit. And what I've plotted on this slide, students, is we have the primary side voltage of our transformer, which we can see is a very nice sinusoidal input, that's Vp. And here I have the output voltage plot from the rectifier part of our circuits. So that's the output voltage here and over here for the various circuits. And as you know that we have these gaps in our output voltage, which is caused due to the positive and negative half cycles, as well as the diode on voltages. If you go back to your lectures on the half wave rectifier and the full wave bridge rectifier, you'll see exactly how we derive these output voltages from our two rectifier circuits. And it's important to note the big difference between these two outputs is the frequency. So we can see that looking at our primary side of our transformer voltage, our frequency here is the same as the frequency of the half wave rectifier, but here for our full wave bridge rectifier, we see that the frequency is double that of our primary side transformer input voltage. Now students, we start off by examining the first stage of our capacitor filter, and that is the charging phase of this. Now looking at our half wave rectifier circuit, we know that the equivalent circuit, when we forward bias the diode, we replace the diode with the diode on voltage source. And when we look at our full wave bridge rectifier, we do the same thing. And in the full wave bridge rectifier, we have two diodes which are conducting and two diodes which are non-conducting and switched off. So now, students, when we are forward biasing our diodes in either of these rectifier circuits, we know that the output from the rectifier waveform is indicated by this purple waveform, which we derived in the previous lectures. And now that we've added a capacitor filter in parallel with our load resistor, what we see happening, students, is that very same voltage that is applied across the load resistor is applied across our capacitor. Remember, they are in parallel, and what this does is it charges up our capacitor. And we can see that when we examine the waveform. And on the waveform's rising edge, we have our capacitor charging plot indicated by this red curve. And we can see that I've plotted our capacitor charge exactly on top of our V output. And there's good reason for that, students, because as I've mentioned, it is at this point in time that our capacitor voltage is equal to the output voltage that we usually see across our load resistor. And here we can see I've indicated it, V out is equal to VC. And what we see happen is this voltage, it rises from 0 right up until a point where the capacitor voltage is equal to the output peak voltage. And we know that we derived an expression for the output peak voltage in previous lectures. And for the half-wave rectifier, the output peak voltage is simply the input peak voltage minus the diode on voltage, because we have one forward bias diode. And for the full wave bridge rectifier, the output peak voltage is equal to the input peak voltage minus 2 times our diode on voltage, because we have two diodes which are needed to be turned on and forward biased in the circuit over here. Now, students, looking at this charge time, which is T charge, that's the time that it takes for our capacitor to charge up, we can actually calculate that. And what we notice is we actually have a very short charge time for our capacitor. And that's because when we examine the charge time constant, which is given by this expression, tau charge, it's equal to the diode resistance multiplied by our capacitor value. And because we know our diode resistance is very small, in most cases less than 50 ohms, that's why we have a very short charge time. So to recap what's happening on the slide, we are forward biasing our diodes in our rectifier circuits. So that means we have a current ID which flows through our diodes and which would usually go through our load resistor only, but because we've put our capacitor filter in parallel with it, we see that that current causes our capacitor to charge up, and the voltage across the capacitor is the rising edge of our output, and it is exactly equal to that rising edge of the output, and we can determine this time that it takes to charge from 0 up until a peak value of V out peak, which is given by these expressions which we derived in previous lectures. Now let's look at the second stage of our capacitor filter circuit, students, and that is the discharge phase. Now the first thing you're going to notice is that we've got equivalent circuits where we have replaced all of our diodes with their open switch model, which tells us that our diodes are, in this case, all reverse biased. Now why do you think that is, students? Well, let's take a look at our output waveforms. Now, initially, when we examined our charging cycle, we knew that our capacitor voltage was exactly equal to our output voltage on the rising edge, up until it reached the output peak voltage. Now, what happens in the circuit here, students, is the capacitor holds the voltage across the load resistor and then discharges it across our load resistor. So from our output peak voltage, our capacitor holds the voltage across the load resistor and then discharges it across the load resistor. Now, while our capacitor is discharging that across our load resistor, we see our output voltage, which would normally have simply gone onto this falling edge, decrease, and that gives us an indication of what's happening at the input voltage. And that's why we know that the input voltage now, because it's going to have a falling edge, is going to be less than the capacitor voltage, which is being held across our load resistor. And now we know that the N side of our diode is going to have a voltage which is greater than the P side. That means our diode is in a reverse bias state. And that's why we replace it with the open circuit equivalent model. So the resultant circuit schematic that we see here for the discharge phase of our capacitor filter circuit is we replace all the diodes with an open circuit, and all we are left with is our capacitor filter and our load resistor. And the current that now flows in the circuit is the current IL, which is the load current, which is generated from our capacitor discharging across our load resistor. And if we look at the time that it takes for our capacitor to discharge for either our half-wave rectifier or our full-wave bridge rectifier, we can determine that discharge time constant, which is simply tau discharge, is equal to our load resistance multiplied by our capacitor value. So students, to recap what's going on this slide, this is the capacitor discharge phase. During this phase, we replace all our diodes with an open circuit because we know they are reversed biased. Why are they reverse biased? Well, they are reverse biased because our capacitor filter holds the voltage across our load resistor, and while it holds the voltage across our load resistor, it slowly discharges it from that point. And while it is discharging it, we know that our input voltage on the P side of our diodes, well, that's going to have a falling edge similar to our output peak voltage, and because that falling edge has a much greater slope than our discharge of our capacitor, eventually our capacitor voltage will be greater than our input voltage, and that reverse biases our diode. Students, this slide, I don't want you to be concerned about the half-wave rectifier circuit. This slide is specifically for our full-wave bridge rectifier circuit. And the reason for that is in our half-wave rectifier circuit, we are still in our discharge phase. But if we look at our full-wave bridge rectifier circuit, from our discharge phase, our capacitor has been discharging, and it now hits the next rising edge of our output voltage. And we know that this next rising edge of the output voltage is caused by the negative half cycle of our input. And that's why we see that the frequency of our full wave bridge rectifier is double that of our half wave rectifier. So our capacitor, to recap, it charges from 0 up until the output peak. It then discharges because our diodes are switched off. And now we are at this point where we're hitting the next charge cycle for our capacitor. Now, because we know that this is the negative half cycle of our input voltage, the diodes that are going to be forward biased in this case are D4 and D3, and the diodes D1 and D2 are going to be reverse biased and switched off. So it's very similar to this first charge cycle that we saw, students. In fact, it's not very similar, it's exactly the same. What we're going to see is our diodes are now going to be forward biased. We're going to have a diode current which flows actually from this point through our circuit. That diode current is then going to have some current going into the capacitor and some going into the load, and that's going to now charge our capacitor for this next rising edge, which is caused by the negative half cycle. And of course, now we can see that our capacitor voltage is exactly superimposed on the output voltage. And yes, you guessed it, that's because the output voltage is equal to the capacitor voltage during the charge cycle. And we're simply going to charge once again all the way till we hit our output peak. So VC, which is our capacitor voltage, is going to equal our output peak voltage. And we can also check that we know that we have a very short charge time, and the charge time constant, tau charge, is simply our diode resistance multiplied by our filter capacitance. Now students, once again, we're going to focus on our full wave bridge rectifier circuit, because we know that in our half wave rectifier circuit, we are still in the discharge stage, and that's because we are only looking at one cycle or the period of the input. So looking again, students, at the full wave bridge rectifier, now that we've charged up once, we've then discharged, we've charged up a second time, well then obviously we now need to go back into the discharge phase. So you see, students, it's a very simple thing, this capacitor filter circuit. It has two phases that it can be in, the charge phase and the discharge phase. And in our charge phase, we know that our diodes are forward biased. So our output voltage is equal to our capacitor voltage. And during the discharge phase, we know that our diodes are all switched off and they are all reverse biased. And our capacitor filter holds our voltage from our peak voltage and then discharges it across our load resistor. And it discharges it up until a point that it hits the next half cycle. And when it hits that point, it then re-enters the charge phase. And as we know, in the charge phase, again, our output voltage is equal to our capacitor voltage because we're charging up our capacitor up until a point that we hit our output peak voltage. And then again, we start discharging and the cycle repeats itself over and over again. And that, students, is essentially how the capacitor filter operates in our rectifier circuit. And we can see that real big difference between the half wave rectifier and the full wave rectifier is really the discharge time. We can see that this discharge time is much longer compared to our full wave bridge rectifier, where it discharges for a much shorter period of time before it enters the next charge cycle. Now, of course, that means we're going to be getting quite a bit more power across our load resistor. And students, please remember the equivalent circuits during the charge phase and the discharge phase. To remind you, when we are charging, we are forward biasing our diodes. So we replace them with the constant drop model. Every diode gets replaced with a source. That's for both the full wave and the half wave rectifier. For the full wave rectifier, during the first charge phase, it's diode 1 and diode 2. Then we go into the discharge phase. And in the discharge phase, we know that all our diodes are reverse biased. So we simply switch them all off. And the equivalent circuit is just this capacitor and our load resistor. Students, the next thing that we want to consider with our capacitor filter circuit is what's happening with our currents. So here I've given us a plot of our output from our rectifiers, followed by the output from our capacitor filters, and then, students, I have the diode current and the capacitor current. And here you can see that I've given this for a full period plus half a period. So we're looking at 1.5 t for these plots over here. So looking at our diode currents, starting off first, we know that during the charge phase, we're going to get our diodes all forward biased, which means they are all going to be conducting and there's current going to be flowing through them. And that's why we see this yellow plot, which kind of looks like a triangle. And we call this a pulsating current that we see flowing through our diodes because it pulsates during each charge cycle. And of course, students, because during the discharge cycle, our diodes are all switched off, that's why we don't see any current flowing here for our discharge cycles. That's why there's absolutely nothing here for our diode currents. And when we look at our capacitor current, students, during the charge cycle, we know that we're going to see the same current that is going through our diode, going through our capacitor, because that is the current that is going to be charging up our capacitor. And of course, then during the discharge phase, our capacitor is going to discharge a current through our load resistor, and that current can be indicated by this yellow rectangle as the current which is discharged into our load resistor during the discharge phase. And that discharge current, students, can be given by I out DC. So that is the DC output current which our capacitor then discharges through our load resistor. And another thing to note, students, is the diode peak current that we see. So the diode peak current occurs during the charge cycle, and when our diodes are forward biased, they are going to experience some peak current, and we'll look in a future slide to see that that peak current needs to be kept at a specific value so that we don't end up damaging our diodes. Look a bit deeper into what's happening with our charge and our discharge on our capacitor filter. So specifically really this diagram or this plot over here, our capacitor current. So students, if we do an approximation on this plot over here, that's why I've written your charge approximation. I know that the charge for this charge cycle, this plot that you see over here, you see there I've given it half T charge multiplied by ID peak. Now that, students, is an approximation that takes this first yellow curve and approximates it to be a triangle. And that's why we see that that equation is actually half base times height, which is the area under this triangle. And that's how we calculate the charge during the charge cycle. Similarly, if we look at the charge during the discharge cycle, we've got a rectangle. So we simply take length times breadth. That's why I have T discharge multiplied by the output DC current. Next, students, we know that there is the conservation of charge, which means that charge cannot be created or destroyed, which means that all charge that is acquired by our capacitor during the charge cycle must be released during its discharge phase, which means that the charge during the charge cycle is equal to the charge during the discharge cycle. So we can simply equate these two equations over here. And when we equate these two equations, we can simply rearrange them to make the diode peak current the subject of the formula. And that's where we get this expression 2.11. It's a very important one, students, which we use to calculate our diode peak current. Now, an important thing to note from this formula is the relationship between our diode peak current and our charge time, T charge. What we see here is that if we have a very fast charge time, we're going to experience a very high peak current. Whereas if we have a very slow charge time, we're going to experience a low peak current. And this means that when we are speccing the diodes for our rectifier circuit, we must always ensure that the diode peak repetitive current is not exceeded by this diode peak current, which is calculated from our charge time. Very important, students, calculate your diode peak current, go to your data sheet and check that it does not exceed the diode peak repetitive current, because if it does, you're going to damage your diodes, and then the best place for them to be put is in the bin. Now, students, looking at the discharge time of our capacitor, we know that the discharge time constant, tau discharge, is given by the capacitor multiplied by our load resistor. Now, the thing about our discharge time, students, is we can actually manipulate it according to the size of our capacitor. So basically, students, here we have on this first plot a very slow discharge, which is given by capacitor C1. And on the second plot, we have a much faster discharge, which is given by capacitor C2. So you can see it takes a long time for this capacitor discharge before it hits the next half cycle. Whereas here it's much quicker, it hits our next half cycle much quicker for capacitor C2. So if we have a bigger capacitor as our capacitor filter, we're going to have a slower discharge. And we look at our change in voltage, which is our VC max versus our VC min. This change in voltage here is also known as our ripple voltage, because our voltage across the capacitor ripples between these 2 points, as you can see. And we can see that if we have a much bigger capacitor, which gives us a slow discharge, we're going to have a ripple which is not very big. So our ripple is going to be quite small, which is going to be closer to a DC straight line. But if we have a much smaller capacitor, we're going to have a bigger ripple because we're going to have a faster discharge. So this bigger ripple from VC max to VC min is going to be a bit further away from what we're looking for, which is a very nice straight line for our DC output. Right, so students, now looking at our capacitor ripple voltage, which is the voltage between our VC max and our VC min when we look at our capacitor filter output indicated by the red curve. We have this derivation on the right, which is used to derive our ripple voltage eventually here at the end, expression 2.12, where our ripple voltage peak to peak is equal to our output peak voltage divided by the frequency multiplied by our capacitor value and our load resistor value. Now students, I'm not going to take you through this derivation, but please look at it in your own time and familiarize yourself with the steps. What I really want you to look at in this slide is the output DC voltage, which is this straight line or dashed line that you see over here. Now the output DC voltage, as we can see, can be calculated by VC max minus a half V ripple peak to peak. So we have our VC max over here, and if we simply subtract half of our ripple peak to peak, we end up at our output DC voltage. Or students, we could even go our VC min, and we could add our half V ripple peak to peak, and if we add our half V ripple peak to peak, we will then come up to our output DC voltage. And also students, important to note that the time period of the output from our capacitor filter is given here, and this time period is for the full wave bridge rectifier circuit, and we can see that we have our discharge time indicated over here, and we have our charge time indicated over here, which is superimposed onto the rising edge of this half cycle. And of course our discharge cycle, that's not the same as our output voltage, because our capacitor holds the voltage and discharges it across our load resistor. Students, when we are looking at our ripple peak to peak voltage, which was derived in the previous slide, the frequency value, if you are working with a half wave rectifier circuit, make sure that you use the same frequency as the input frequency. But students, if you are using either of the full wave rectifier circuits, make sure that the frequency you are using is equal to 2 times the input frequency. Now finally students, I'm going to take you through some of the capacitor filter design steps. Now when you are designing a capacitor filter for your power supply, the first step that you want to take is to express your ripple. So the ripple is an expression that you have to give. You as the engineer decide on this value. And there are 3 ways that you can express your ripple voltage or your ripple. The first is your peak to peak ripple voltage. That's that expression that we derived. Alternatively, you can express it as a percentage of the peak output, or students, you can express it as a percentage ripple factor. Now once you express your ripple, or you rather choose what you want your ripple to be, you want to then actually calculate your capacitor value. Now again, you can go back to equation 2.12, which is V ripple peak to peak is equal to this right hand side, and we rearrange it to make our capacitor value the subject of the expression, and we know what all these values are. We have already determined, or rather chosen, what we want our ripple peak to peak to be. We know what our output peak voltage is. We've got our frequency and our load resistance, and we calculate what our capacitor value needs to be. And then finally students, the most important thing, make sure you select a capacitor voltage rating such that that capacitor voltage rating is greater than the output peak voltage that you're going to see in your circuit. If you mess this up students, you're going to see a lot of capacitors exploding and smoking and blowing up. So make sure you select a capacitor voltage rating such that it is greater than your output peak voltage. Now looking a bit closer at our percentage ripple, what exactly is percentage ripple? Well students, percentage ripple is simply given by this expression, which is our ripple RMS divided by our output DC voltage multiplied by 100%. And if we are to calculate our ripple voltage RMS, that's this expression over here, which is simply our peak to peak ripple value divided by 2 root 3. Now students, why is it that we are not multiplying it by 2 root 2? Because if we have a sinusoidal wave, we know that we take our peak to peak and divide it by 2 root 2 to get our RMS voltage. But in this case, students, we take 2 root 3 because when we look at the capacitor filter output, it's not actually a sinusoid. it actually looks more like a triangular waveform. And because it looks like a triangular waveform, we replace the root 2 by root 3 in order to calculate our ripple RMS. And then finally, students, our output DC, we know what that expression is. It's simply our output peak minus a half multiplied by our voltage ripple peak to peak. And now, students, finally for this lecture, we're going to do a quick exercise. The AC input to a transformer is 230 volts RMS at 50 Hertz. The peak output voltage across the output of the circuit is 20 volts, and the load resistor is 100 ohms. Suppose the input capacitor filter is 1000 microfarads, and determine the following. So here we have our circuit. At least they didn't ask us to draw the circuit, thank God. The peak-to-peak ripple voltage, then we need to find out our voltage rating of the filter capacitor. We then need to determine the ripple factor. We then need the maximum reverse voltage across a non-conducting diode. We then need the peak inverse voltage, and then finally transformer turns ratio. I think this is going to be a quick and easy one. Let's take a look. Okay, so first up, the peak-to-peak ripple voltage. Well, that's a simple one. We use expression 2.112. And we simply substitute in all these known values, and we get 2 volts out. A thing to note for this one, students, you can see here for the frequency, I have 2 times 50, because by the looks of it, we've got a full wave bridge rectifier circuit. So we know that the output is going to have a frequency which is double the input. That's why I have 2 times 50 here for our frequency. Next up, what is the voltage rating of our filter capacitor? Well, we know that the rating of the capacitor must be greater than our output peak voltage. So if we have a capacitor that is rated at least 20 volts or more, we'll be good to go. Next up, they want the percentage ripple factor. Well, again, that's a very simple one. Students, we have that expression over here, which is the ripple RMS divided by the output DC multiplied by 100%. And if we then substitute in our ripple RMS expression, and our output DC expression over here, multiplied by 100%. We know all these values, students. 3% is what we get for our percentage ripple. Next up, maximum reverse voltage. That's basically the biggest voltage a non-conducting diode is going to see on the N-side terminal. And we know that that's going to have at the peak or the negative peak of our input. So that's why our MRV is equal to minus V in peak plus our diode on voltage. But now, students, we don't have any input peak voltage given. So we know that our output peak can be expressed by our input peak minus 2 times VD on. And that is the expression for a full wave bridge rectifier, which we derived previously. So using that expression, we rearrange it to make V input peak the subject. Then we have an expression for V input peak, which we can substitute in here and simply calculate our maximum reverse voltage to be minus 20,7 volts. Next up, students, we need to specify the rectifier diode peak inverse voltage. We know that the peak inverse voltage is our breakdown voltage, and we need our peak inverse voltage to be greater than the maximum reverse voltage. Because if it isn't, our diode is going to enter into breakdown state, and we don't want that to happen. So our peak inverse voltage when we're speccing our diode must be greater than the magnitude of our maximum reverse voltage. We know what that is, so the magnitude of negative 20,7. And finally, students, the turns ratio. Turns ratio, this isn't a center tap transformer, it is a normal transformer. So it's simply the primary voltage divided by the secondary voltage. Of course, always make sure that both voltages are either in RMS values or in peak or peak-to-peak values. Make sure they're all the same. So here we are simply converting our 230 volts RMS into a peak value, and we divide it by our secondary voltage, which is our input voltage, and we get a turns ratio of 15. That brings us to the end of lecture 9, students. A quick recap: we looked at the power supply again. I then showed you the capacitor filter schematic for all of the rectifier circuits. We simply put the capacitor in parallel with our load resistor. We then looked at the filter operation, and we saw that it basically has two states, which is a charging state and a discharging state. While the capacitor is charging, we know that our diodes are forward biased, and when our capacitor is discharging, we know that all of our diodes are reverse biased, so they are simply open circuited. We then looked at the filter currents, and we used the conservation of charge to derive an expression for the diode peak current. And we know that diode peak current is inversely related to the charge time. And we need to ensure that we don't exceed our diode peak repetitive current when selecting a diode or designing our filter circuit. We then derived an expression for our filter ripple voltage. This is quite a hectic derivation that I've asked you to look at in your own time. Please, students, take a look at that. And then finally, students, I took you through how to design your filter circuit from selecting or expressing your ripple to selecting or calculating your capacitor value, and then making sure that your capacitor voltage is not exceeded by the output voltage of your circuit. And students, if you're still confused or you don't understand something from this lecture, please take a look at your textbook, chapter 2, pages 75 to 81, and come and talk to me in the lecture enrichment sessions. If there's any criticism or constructive feedback, any questions, students, I'm here to help you. Thank you.